Hello, my name is Gregory del Rosario, and I am a member of the Dingleberries, and I will be your narrator for this film. So I know you may be asking yourself, what is the Automatic Piano Project? In essence, the Automatic Piano Project is designing and developing an automated piano player that can play ASCII files. Professor Ziding felt it appropriate to create a capstone project to apply not only the concepts of programming but to test our ability to think on our feet, the ability to analyze a foreign problem and solve it with the resources at hand. The project was assigned, and we were to create a team of 2 to 3 students to tackle one of 3 projects. Of the 3 possible projects, we selected the one known as the Automatic Piano Player. Our task at hand was the following: to use the tools in MATLAB to synthesize a text file of a given format, given the waveform generated by the parsed text, and then play this waveform. This waveform is then to be further processed and refined using techniques such as attack and decay, change of tempo, the option to add emphasis in certain beats. In essence, our task was to create a functional piano synthesizer. In addition to this task, our program had to be flexible enough to handle certain user interactions, ranging from changing the tempo to playing the music measure by measure or continuously. With the brief background in mind, we will now continue on to how we accomplished our task. Now, let me assure anyone watching this video that this program did not suddenly appear magically as, say, a rabbit out of a hat. It certainly took many hours of work, planning, and coordination between our team, and we believe that coordination was the key to our success. Almost immediately, our team began to formulate ideas on how to attack this problem. Along the way, we began to also contemplate the barriers or problems that we would encounter at each key point given. As any good team, we spent a great deal planning our schedule, establishing necessary communication and file sharing techniques, while divvying up the assignment at hand. Through the interim report, we created a comprehensive timeline which detailed throughout the month of November and the beginning of December what point in the program we should be in order to reach our goal of completing a finished product on time. Our completed MATLAB code requires the following files in order to operate. The files include music.r.txt, which is a text file of the right-hand melody of the song Heart and Soul by Hoagie Carmichael, musicleft.txt, which is the melody for the left hand, formatter.m, frequency.m, playsound.m, formatarray.m, and finally piano.m. The following M files are going to be described later on in this presentation in greater detail along with screenshots. The format given to us for this project was the following: X, Y, M, K, T. Using this format for parsing text, we were to create an ASCII file, which is our music file, of a song using the X, Y, M, K, T format. As you can see by the screenshot on the screen, X can be A, B, C, D, E, F, or G, as in a standard music note. X is for flat, sharp, and for normal. M can be 0, 1, 2, 3, 4, 5, 6, 7, 8, representing the octave number. K can be 0, 1, 2, 4, 8, for 4 levels of amplitude from soft to loud. And finally, T can be 1, 2, 4, 8, for full note, half note, quarter note, and 1/8 note. The first function we'll be covering in this report is formatter.m. Formatter.m takes the input from the main script, which in turn was from the 2 text files. The input is then put into a readable format by the script. In our case, we remove white spaces from the input file, as demonstrated by the while loop. Similar to the format.m, format array takes the script in the input and converts it from a string to ASCII characters. From there, the script determines the location of the commas and deletes them. This allows for the input to be placed into a character array after reconverting back to char from ASCII. The array is organized such that a row only contains the 5 components of a note. Each row represents 1 note. The frequency script is a function which takes the input from the main script and places the frequency data into a tidy MATLAB array organized by note, letter, type of accident, and octave number. Similarly, this frequency data can be retrieved using the same information. The frequency of the note is subsequently returned to the main function. At the top of the play sound script, which is highlighted above, it sets the frequency to 44,100, creates the period, creates the duration of the note, creates a sine wave for the vector, and then creates an array of the sound vector to be returned to the main function. It also determines the patch and volume of the notes. Furthermore, this function is responsible for the implementation of the ADSR envelope, which is supposed to make the notes sound more natural. There are 4 ADSR schemes, one for each type of note. This is highlighted in the body now. We decided to increase the duration of the sustain period for the longer notes and shorten the rest. Finally, we had to implement a length check because the number of elements in the ADSR envelope would sometimes be larger or smaller than the note vector, generating an error message. The length check adds a negligible element of value 0 to the end. Our final script is piano.m, which serves as our main script. This beast of a file weighs in at over 443 lines of code and handles everything from parsing user text to implementing said text into functions, which were covered before. In this video presentation, I will not cover the full functionality step by step of this piano script, so instead I will actually show you when the script is run what is outputted. Upon running the main script, you will be prompted in the command window with the following questions. The first being, please enter the number of input files you wish to use, 1 or 2. Please enter the name of the first file. Please enter the name of the second file. If you want to play the song continuously, how fast you would like the song to be played, and do you want emphasis on the first and third notes in each measure. And in this sample case, we are doing 2 files, one of the right hand, one of the left hand. The song is played continuously, at normal speed, with emphasis on the first and third notes in each measure. Now, without further ado, I present to you Hoagie Carmichael's Heart and Soul via MATLAB. Hello, Greg here. Yes, I'm the guy whose beautiful voice you've been listening to for the past 8 minutes. Because of this, I'll try and keep this brief. My reflection for this project is one of a truly unique experience. Because of my role as a support programmer, lead report editor, and video editor, I had to take on a systems engineering-like role where I knew a little about everything. Because of this, I obtained an appreciation for helping put this project together and having a view of the larger picture and all of the planning it takes to put together a successful project.
This is Joel Mendoza. I'm a second-year UC Davis student. I was part of the Dingleberries-Engineering 6 project. I worked on the main script, sample text files, and attack and decay problem. I'm just going to run a couple of the functions I came up with, and I'll try to explain them. This is the attack and decay function. Which pretty much just makes a graph that constrains or bounds each note. This is just to make the sound of each note sound more natural. In the main script, I worked on receiving valid input from the user.
Hi, my name is Jeffrey, and I did the majority of the programming for this project. This includes the basics for the piano, pausing at the breaks, plotting the waveform, pausing at measures, changing tempo, changes in amplitude, and emphasis on the first and third beats. I also helped out with the ADSR code, and I also helped clarify many details for the group report. I hope you enjoyed this project as much as we enjoyed making it.